Welcome to the Explainer. Right now, millions of people are feeling the bite of a truly massive winter storm. Today, we're going to unpack the incredible science behind it, and it all comes down to a phenomenon happening miles above our heads that's causing all this chaos down here.
So let's start right on the ground. For huge parts of the country, this is the reality. Just bitter, dangerous cold. After a pretty mild winter for a lot of folks, this sudden blast is a real shock to the system, and it's causing power outages and some seriously hazardous conditions for millions.
And this map, wow, it just shows you the sheer scale of what we're talking about. Look at that. All that pink and purple represents severe weather warnings, and they are blanketing a massive portion of the country. This isn't just some local storm, it's a continental-sized superstorm.
So, what on earth causes a storm this big? Well, it's not just one thing. It's actually more like a recipe, with a few crucial ingredients that have to come together at the exact perfect time.
Okay, so here are the three main components. First, you need that big clash, right? You need bitterly cold Arctic air slamming into much warmer southern air. Second, you gotta have a big southward dip in the jet stream to really steer the whole weather system. And third, you need fuel, and a lot of it, a massive source of moisture to create all that snow and ice.
And that second ingredient, the jet stream, that's the real engine here. You can see it on this slide, that wavy river of air. For this storm, it dipped way, way down, and it acted like this giant atmospheric pump, just sucking up enormous amounts of moisture from an unusually warm Gulf of Mexico. That's what supercharged the entire system.
But here's the thing. The storm on the ground, that's only half the story. The reason this whole event is so powerful and so incredibly cold, well, that secret lies much, much higher up in our atmosphere. The real driver is totally hidden from view.
To find the true culprit, we have to travel way up, way, way up into the stratosphere, far above where our everyday weather actually happens.
So this chart here shows the different layers of our atmosphere. All our weather, the clouds, the rain, the snow, it's all contained in that bottom layer, the troposphere. That ends about 7 miles up. But what happens in that layer can be seriously influenced by the very stable layer above it, the stratosphere. And we're not talking just a little bit higher. We have to go way up to an event that's happening 20 to 30 miles above the surface of the Earth. It's up here that we find the real engine of this cold snap, something called the stratospheric polar vortex.
Now, this is super important. This is not the polar vortex you usually hear about on the news. That one is usually talking about the jet stream down here in the troposphere. This is a whole separate system, way higher up. Think of it like a second, faster jet stream that normally does a great job of keeping the absolute coldest air locked up tight over the Arctic.
So, how does something happening so ridiculously high up end up affecting our weather down here on the ground? Well, it all starts when that super stable vortex gets disrupted.
Okay, this slide is perfect because it shows the two states of the vortex. On the left, you've got a stable, tight vortex. It's like a perfectly spinning top, keeping all that frigid air contained right over the pole. But on the right, that's when you see a disrupted one. It gets all wobbly, it gets stretched out, and that's when the trouble starts, because that cold air can now escape and head south.
Think of it like this. There are these atmospheric waves, kind of like ripples in a pond, that are always traveling up from the troposphere. Normally, they just sort of fade away. But when the vortex gets stretched out, it acts like a wall. That wave energy hits it, and bam, it reflects back down, messing with all the weather below. So this is the crucial point, and you can see it right here. That stretching of the stratospheric polar vortex. That's step one. It creates the absolute perfect setup for that downward wave reflection, sending a jolt of energy right back down toward the jet stream.
And this shot just illustrates the final result perfectly. That reflected energy makes the jet stream way wavier, creating a deep, deep southward plunge. This is basically the atmospheric equivalent of opening the freezer door and letting that massive blob of Arctic air pour out all over the continent.
Okay, so all of this leads to a question that you are probably asking yourself right about now. If the world is getting warmer, why on earth are we still getting these absolutely brutal cold snaps?
It definitely feels like a paradox, doesn't it? It's a great question. But the answer is pretty complex, and it really shows just how interconnected our entire climate system is. It's not nearly as simple as everything gets warmer everywhere all the time.
So get this, it's pretty fascinating. Some research suggests that because the Arctic is warming so rapidly, it might actually be making that stratospheric polar vortex less stable, more likely to have these disruptions. And, at the same time, warmer oceans mean there's more moisture in the air to fuel these storms when they do happen. So while our winters on average are getting milder, the most intense storms might actually be getting stronger.
So the big takeaway here is that even as the planet warms, the threat of extreme cold isn't going away, it's evolving. The nature of winter itself is changing, and it forces us to ask a really important question. How do we prepare for a future where these cold snaps might be less frequent, but pack a much more powerful punch when they finally arrive?